Good morning and welcome to the first lecture of this new course on functional data structures. And let me first give you a very brief overview of what's in store for you in the rest of the term. So, brief introduction. And what is the course about? Well, it's about two topics. The first one is data structures and algorithms, but specifically for functional programming languages. But code is not enough. So the other component of the course, which is at least as important as the code, are the correctness proofs. And not just of the functional correctness of the algorithm, but also of their complexity in some cases. And we're using not pieces of paper, but we're using a machine to conduct those proofs. But don't be mistaken, they won't be all automatic. So we're using a proof assistant called Isabel. What is a proof assistant? The ideal is that you give the structure of the proof, and then the proof assistant checks the correctness and fills in steps that are missing. So you don't have to give all of the detail, but you may have to give more detail than you are used to on paper. The result is this is really a time-consuming effort, and not just time-consuming, it's also potentially addictive. It undermines your trust in your naive proofs because it shows you how often you go wrong. So that's a warning up front. Terminology, when I speak of formal proof in this course, what I mean is machine checked, and when I speak of verification, what I mean is it's formal correctness proof. And these things that you'll see in this course, the kind of algorithm and proofs will be fairly simple, but these proof assistants have been applied to distinctly non-simple things. One is a C compiler that was verified, I think it's now already 10 years ago, and it is competitive with GCC on optimization level 1, and that was done by Xavier Leroy at INRIA in Paris. And this is a continuing project, so people are building on this, and they by now they have all kinds of extensions, like for concurrency and other things. And then there's something quite similar, an operating system microkernel verification that was done also about 10 years ago by Gavin Flynn, who used to be a student here in Sydney. This just shows you, without going into any details, these systems, although we will only apply them to fairly simple problems, can be applied to really complicated pieces of code. So, overview of the course. The first 5 weeks will be dedicated entirely to introduction to the Isabel proof assistant, and the rest of the semester will be roughly the following topics: search trees, priority queues, and related data structures. I haven't finalized the syllabus yet, and their, in some cases, amortized complexity. So this is really the core contents of the course. And what do we expect from you? I expect that you are familiar with the functional programming language in the ML or Haskell style. So there are various ones out there, and it doesn't matter exactly which one you're familiar with. And we are assuming that you are already familiar with the first course in data structure, so I don't have to explain what a search tree is. But I may have to explain what a particular kind of search tree is. And finally, I assume that you're familiar with the course in discrete mathematics, so algorithm analysis and induction and things like that are not new to you. And very important, this course really requires that you do the homework, otherwise you'll get lost very quickly. And that's why also you get already quite a large percentage of your marks are based on the homework, so it pays off to do the homework. That's it. Any questions about the course? General questions? Yes?
Is there a course level lesson and an exercise lesson? I mean, in the morning it's a course, and in the afternoon it's course?
No, it's a tutorial. Okay. So it's exercises. I think it's right after this one. Is that correct? Or another block? What?
I think
break of 2 hours, yeah, yes. Okay, in that case, let's just get started because we don't have that much time and we have a lot of material to cover. So let me briefly introduce you to the basics of Isabelle. We start with a chapter I've called Programming and Proving because it's a combination of writing little programs and writing little proofs. And we'll start with an overview of the system. First, a little quiz, although I'll give you the answer right away. Which of these 3 formulas are equivalent? And it turns out that the first one and the last one are equivalent. And the one in the middle is something very different. And why am I showing you this? Because we will often see formulas of this form, but in fact, you can think of them like that. That's logically equivalent, and that may be more convenient to think of it that way. Notation, yeah, right. Again, about the arrows. Arrows always associate to the right. That's the standard convention, not just for Isabelle. That means if you write this thing here, it really means this. And this is the, that makes sense because this and this really means this. And that's a very typical situation. You have a number of assumptions and you want to prove a conclusion from it. So that's why this is the version. This is how the nested implications pass with the arrows to the right. And it's the same for all the arrows. We'll see other arrows as we go along, and they always have this convention. And finally, I will sometimes show inference rules like this, and this is just a graphical notation for this. So there's nothing special about it. So much for notation. Now we come to the actual system. So what is HL? Isabelle HL. Isabelle is the sort of the mother system, which is a generic system that's not specialized to particular logic, but Isabelle HOL is the specialization to a particular logic, and that's the logic that we'll always be working in. And HOL stands for higher order logic, and it's really, you can just say, what is higher order logic? It's functional programming plus logic. And why the functional programming? Well, because the logic provides for data types, it provides for recursive functions, and it provides for logical operators. So this is where the logical part comes in. The first 2 are the data, the functional programming, and the last part is the logical operators. And it is really a programming language. Otherwise, you couldn't verify a compiler in it. The compiler was written in a programming language like that, in different dialect or different form of higher order logic. And the only point why it's called higher order is that functions are values too. So passing around an integer or passing around a function, it makes no difference. That's just one of the basic properties of functional programming. I would appreciate if people came on time. It may be hard on a Friday morning, but I think it's kind of a courtesy to the rest of us. What are formulas? At the moment, the only formulas we'll consider for the next 1 or 2 weeks, almost the only ones, are equations of the form term equals term. For example, the equation 1 plus 2 equals 4 is a formula. And later then we'll add more operators, although we might slip some of them in already earlier, because I assume that you've seen an and, an or, and an arrow before, so that shouldn't be a problem. So what are the types? Because it's a typed language, all the decent functional programming languages are typed, and the terms are the things that you write your formulas, your programs, your computations with. So what are the types? When you see a tau, you can always assume it's a type. So what's the basic syntax for types? Well, you can put types in parentheses, as always. Then we have a number of base types, and Booleans, natural numbers, integers, and also reals. Those are the only ones that we'll need in this course, more or less, I think. And then we have type variables. In the notation that we're using here, you can distinguish the type variables from the fixed types by the fact that they start with a quote. In other languages, they have different conventions. I will not read out the quotes, so I will just say A, B, C rather than quote A, quote B, quote C, and it'll be obvious from what you see on the slide that it's the type variable that I mean. And finally, we have function types, and here, for certain historical reasons, we're using this double arrow rather than the single arrow, as you would see in most programming languages. And then we also have pairs, and I recommend to avoid them as much as you can, because they typically cause complications for certain logical reasons. So they're there, but if you don't need them, don't drag them into the business. And finally, no, not quite finally, then we have lists. We'll spend quite some time on lists today. So tau list means the type of lists over type tau. So this is the component type tau, and list is the type constructor. In other languages like Haskell, you would write the list first and then the tau as the argument second, list over tau. Here it's the ML family where you write the type constructor behind its argument type. And then we also have sets, sets over the component type or the element type tau. And lists are finite, sets are not necessarily finite. Sets are good old sets as you know them from mathematics. Lists are lists as you know them from functional programming. And then you can define your own types. We'll get to that pretty soon. Questions about types? Right. Then terms. How do you write down a term that means something? As usual, parentheses. And then the terms are built up from constants or variables, but they're just identifiers in the first place. You write down an identifier, and that may refer to a constant, meaning something that you've declared further up, or a variable, meaning something you haven't declared, but you've just introduced locally in this term. Then you have function application. As usual in functional programming, you just put the two terms next to each other. There are not necessarily parentheses there. Then there is function abstraction, the function lambda x dot t, which maps x to the result value t. And then we have lots of syntactic sugar. So in the core of the language, it's really these three things. The parentheses are just syntactic sugar, but then we have the basic items, constants and variables, we have application, and we have what's called function abstraction. And that's what any functional programming language is made of, and everything else is just additional layer of syntactic sugar on top of it. And we'll see, we'll come across, I will introduce that syntactic sugar as we go along, but the core of it is just these three constructs. And that's just known as the lambda calculus. So if you're familiar with the functional programming language, I do assume that your lecturer mentioned lambda calculus. Terms must be well typed, otherwise the type system is kind of useless. What does that mean? Essentially, it means that the argument of every function call must be of the right type for that function symbol. And the notation we're using here is, in this case, borrowed from Haskell. T colon colon tau means that T is a term that is well typed and is of type tau. And the essential rule, the essential inference rule for inferring well typedness, at least for applications, is that if you apply a term T to a term U, then that's well typed of type tau 2, provided that T is indeed a function, otherwise this application makes no sense, and it's a function from type tau 1 to type tau 2, and U must be an argument that is of the right type. Well, that is just the argument type tau 1, and if you put them together, you'll get a result of type tau 2. So that's the essential rule for checking that compound terms are well typed. Type inference means that the system will compute the types of variables itself. So you, of course, when you declare a function, you should give the type. But if you write a term with variables in it, you don't have to give the term of the variable. The type of the variable, the system will infer that. And this is what all of the functional programming languages provide. there is a complication in the presence of overloaded functions, functions which have multiple types. Then this type inference isn't always possible, and you may have to give type annotations to disambiguate your term. So, for example, if there are multiple f's and you want a particular one, you may have to write f and then the argument type, you write x, and then you say, oh, please let x be a natural number, because if you didn't write this, x is assumed to be a variable, and if the context doesn't clearly say or doesn't clearly imply what the type of x is, then it's not clear which f you mean, and therefore here you can put this annotation locally into a term and thus disambiguate the function call. I recommend not to use pairs. I already said this. This is known as carrying, and so the choice that you have, you can either write your function like this in carried form, where the arguments are given to the function one by one, or in tupled form, where the arguments are given as one big tuple, and I strongly recommend to use the carried form. That has many advantages. Then predefined syntactic sugar. There's lots of it, in particular infix symbols, like the ones that you know from everyday programming in mathematics, plus, minus, times, but also hash and append, at sign. I'll introduce them one by one when we get to it. There is mixed fixed syntax, that's already good to know now. We have an if then else. If Boolean condition, then one value, else another value, and we also have case syntax for structured data types to take values apart. Important, never forget if you mix infix and prefix applications, so f of x is prefix application because the function is in front of its argument, plus is of course infix. If you mix that, the prefix binds more strongly than the infix, so if you write this without any parentheses, this is what it's meant. This is again standard convention from functional programming, there's nothing specific here. There is something specific in Isabelle. The parser expects if then else's and also cases to be in parentheses. So if you don't do that, then basically the parser is confused about where your else ends, and therefore please always put the parentheses around it, otherwise you get usually parser errors. So that's, yeah.
Ich habe noch eine Frage. I have a question.
Yeah.
Like we used Okame in our I2 course, and I wanted to ask if you can refer to the infix operators in a prefix function.
Yes, you can, and sometimes this is useful. So if you have let's just take a plus. If you write op plus, then that is the prefix function. And in fact, that happens when you get an error message. The system will typically print out, if there's something problematic about the plus symbol, it'll talk about op plus, and that's the prefix version of it. So just for those of you who didn't quite follow this question, you can, instead of writing A plus B, you can also write op plus AB. Not that that is terribly helpful, but it is helpful at the point where you omit the A and the B, and then this is still a well-formed term where you have just given the first argument to the plus, which you can't do in infix form. You can't just write A plus and then nothing.
So is op plus already a carried function?
Yes. All the basic functions are carried by default. So, yes, and I encourage you to ask such questions. Now we come to that was the sort of the small picture. Now we come to the big picture. How do you put together larger chunks of terms and types and whatever? And these are called theories. And you can think of them as a module. A theory is a module, and it's just called a theory because the content is a mixture of mathematics and programming. And this is the syntax. Keyword theory, then the name of your theory, then the imports list, all the other theories that you're building on, and then between begin and end, you have a list of definitions, theorems, and proofs, because there's also other stuff, but the Holy Trinity is definition, theorem, proof. And this is, of course, where we'll spend most of our time explaining how to write definitions, how to write theorems, how to write proofs. Now, for your purpose, please, unless we say something else, always just import main. Because what is main? Main is basically a large theory that's predefined, that provides many things that you're used to from mathematics, like all the types I showed you, the lists, the sets, the booleans, the numbers, and many, many lemmas about them. And this is the default starting point for all of your work, unless we give other hints. Yes, there is a concrete syntax point that I need to mention. I didn't say this. If your theory has a certain name, then the theory must live in a file with the extension .thy. So that's a default convention. Your theory name and the file name must agree, but the file name has the extension .thy. And so if you have these theory files, in there, your types and terms and formulas need to be enclosed in double quotes. There's essentially a kind of two-level grammar. There's an outer level. You can already see it here. There's an outer level which has keywords like theory and imports and begin and end. And then there's an inner level of logical formulas. This has got nothing to do with logic. This is just some grouping syntax and naming. But the actual formulas for writing down recursive functions or writing down formulas, that is needs to be enclosed in double quotes. That's just a convention we have, and you'll see it in all the examples. Except for single identifiers there, you can drop the quotes around them. And I think on the slides I will often drop them, maybe not initially, but later. And in the files, of course, you can't drop them. You have to put them there. So how do we interact with the system? Well, there's a nice interface called Isabelle JEdit, and it's called JEdit because it's based on an editor called JEdit. And what it does, it processes your text automatically. So when you open a file, it starts processing the text that's already in there, or as you type it, it already processes it after a fraction of a second after you've typed it. And it's like modern Java or other language IDEs that try to give you feedback as quickly as possible. And let me show you this right away with a little demo of the system. We're not proving anything or programming anything yet, just a little interaction with the system. Where are we? I think I want this one, yes. These files are also in the we have a repository with all the material for the course, and the files that I demo here are part of that repository. So you can look at them later on. So this is, let me just first close this. So this is the main window onto a theory called, in this case, overview demo, and it just imports main. And first we have a few comments in various forms. That's not so interesting. And then here on this line, we have something we just call a diagnostic command called term. The term just reads in a string and tells you what it thinks of the string as a term. So it doesn't really do anything. It just reads and echoes what it has made of that term. And now, in order to see what the output is, you can either hover. You can see there's some gray underline under the term, which means there's some output that you can get to by hovering on it. But to be honest, I never do that, so I'm kind of confused what the best way to get at the output is. I click on output, then you get a second window, and there you can see the output. And here, the output to your input is, it echoes your input, and then it says, oh, and by the way, I've inferred that this is of type bool. So here you've already learned that there's a constant called true of type bool. And similarly, there's a constant called false of type bool. Unsurprisingly, but it's important that that the names start with capitals, because if you let them start with lowercase t, for example, as in true, then it won't say it's of type bool, it'll say it's of type A. Why? Because it hasn't seen little lowercase true before, and so it assumes it's a variable, and it's of an arbitrary type. And you can detect the difference already by the color, because the true and false with capital T and F, they're in black, so that is an indication they are recognized as constants, where something in blue is an indication, I haven't seen this before, I'll assume it's a variable. So do watch out for the colors. Here is a more complicated term, true and false. So here you can also see one of the ASCII syntaxes for and, the ampersand symbol. And here you see actually what it echoes is different from what you input, in that the echo is pretty printed and it uses the mathematical symbols rather than any ASCII replacement syntax. And if you type in true and false, and the false is in lowercase, that still makes sense, except that one of them, the true, is a constant, and the other one, false, well, you've called it false, but it's just an arbitrary variable. And you can always figure out which is which by hovering over part of the term. So if you hover over for example, this true, and you press, in my case, the command key, it says, oh, this part is a constant. It's called whole true, which means it was declared in theory whole, and the name is true, and it also gives you the type. And if you now hover over the false, then it says, oh, this is a free variable of type bool. So you can also go to parts of your formula and find out what the system made of them. And you can also try and evaluate terms. So here, for example, the question is, what is the value of true and false? And it's false. Now, you can basically put in any term here, and sometimes it makes sense to have a value to get. Sometimes it's possible to get a value out of it, and sometimes it isn't. You could also write a quantified formula. For example, you could ask, what is the value of, there exists an x such that x squared is greater than x. The system is not going to give you a value for that. But if it can evaluate things, then it will do so. So if things are computable, like and or, then it will compute with them. If they're not computable, like quantifiers, then it won't do anything. So, but it can also it can sometimes compute with terms that are partially instantiated. So this next term, true and p, it can compute with, and it says it's just p, where p is a free variable of type bool. And so sometimes it doesn't need all the information. It can also work with symbolic terms. But that's about kind of if you're lucky. So. Yes, this is just what I said. And sometimes the types are not inferred uniquely. So, for example, if you ask if you give the formula n plus n equals 0, and you go there, and then you ask, well, it inferred that it must be of type bool because it's an equality. But what about the type of n? If you now hover over the n, it'll say it's a free variable of type A, because there's nothing in the term to force n to be of any particular type. So it'll assume that it's an arbitrary type A because the plus symbol is overloaded. But on the other hand, if you say explicitly n is of type nat, then, as in the next line, then that will propagate throughout the term. So if I ask what's the type of that n, it is really a free variable of type nat. Yeah. So I'm just noting that whenever you deal with numbers, things are overloaded, and you have to sometimes give more information to make sure that the system chooses the right type for the variables. Yes, and that's really all that I want to show. Then let's get back to the slides.
So does the theory main import HOL in it?
Main has HOL in it, yes. So now by example, I want to introduce the basic types that we'll be using over the next, over this semester, bool, nat, and lists. This is not really a basic type, it's a type constructor, but bool and nat are base types, and they're absolutely essential, and of course, functional programmers need lists. So first type bool, this is how the type bool could have been declared. It's not really done that way, but in principle it could do it. This keyword data type comes from standard ML. Other languages like OCaml use type at that point. Other languages like Haskell use data. We use data type. So it introduces a new, potentially recursive data type on the left, and here on the right you enumerate the different constructors of how to build values of that type. And here there are only, it's just an enumerated type with two constructors, true and false, and so there's not much more to say about it. And then the system already has a lot of predefined functions, so and, or, arrow, and other stuff are just functions on booleans. They take two booleans and give you another boolean. There's nothing special about them. And a formula is simply a term of type bool. So there's not really a special syntax for formulas. Anything that is of type bool is considered a formula. And one difference to the usual mathematical syntax, we also have an if and only if operator, and that is simply the equality. So if you write an equality between two Boolean terms, that's just the same as writing if and only if, the double arrow. Next one up, natural numbers. So natural numbers are represented with 0 and successor. So this is the data type, how the natural numbers are introduced. A natural number can be either 0 or it can be suc of a natural number. And that's how you represent all natural numbers. So values of type nat will certainly be 0, and then successor of some natural numbers. Well, we only have 0 so far, so successor of 0, but then we can build suc of 0, and so on. So that's how you get all the natural numbers. This is not a very efficient representation, but it's a logically very convenient notation. And so internally, in fact, if you write a large numeral like 4 million, then internally this will be converted into binary representation. But logically, the view of the natural numbers is this. And sometimes you may have to convert between the 2 points of view, but I recommend just simply most of the time to stick to this representation and don't worry about efficiency. Then there are a number of predefined functions like addition, multiplication, and so on, and they are binary functions of type nat to nat to nat. And as I already indicated, numbers and arithmetic operations are overloaded, so even if you write 0, it could be 0 of many different types, and so it'll just get that in arbitrary type A, and similarly for plus, it has, in fact, not this fixed type, but plus is overloaded and has this generic type. Now, for those who are familiar with type classes, in fact, there's a type class system behind it, but we don't need to go into it. I'll just use this generic term, overloaded, and that is sufficient. So you may need these type annotations like saying, oh, please take the one of type nat, or here in addition, and please y must be a natural number, unless, of course, the context forces that anyway. So, for example, if you write suc of z, then z is automatically a natural number because suc is not overloaded. Suc is really only defined on natural numbers. So if you write suc of z, z will automatically be inferred to be a natural number. So brief demo of natural numbers. And this is the first proof that we'll see. So you can see two things in this little theory. First, the definition of a function, and then the statement and proof of a little lemma. And so let's start with the function definition up there. So this is the standard syntax. You introduce a function with the keyword fun. That's a potentially recursive function, name of the function, colon, colon, and then its type in double quotes, because it's a non-atomic type. It's a big type, so it needs those double quotes around it. Then keyword where, and then come a sequence of recursion equations separated by the vertical bar. And so here we define addition by recursion on the first argument, and if the first argument is 0, we return the second argument. And if the first argument is suc of m, which you can think of as m plus 1, except that we haven't defined it, we're just only in the process of defining plus 1. So if you have a successor here in the first argument, then you add together m and n, and you make the successor, you add the 1 afterwards. So this is, in fact, probably something like 110 years old now. These are the Peano natural numbers. And now we want to prove a little lemma, and this is the structure of the statement. You have the keyword lemma, then you have the name of the lemma. Lemmas should always have names, otherwise you can't refer to them. And then the statement of the lemma. And the statement of the lemma is that if you do addition and the second argument is 0, then the first argument is returned. And that's not something that follows that's just an equational consequence of these two rules, but something that needs an induction. And so what we're proving now is, we're proving in this next line, we say, in order to prove this lemma, please use induction, and use induction on the number m. In this case, there isn't much of a choice. There's only one variable in there, but you always have to explicitly say what you're inducting on. And then we call the auto-proof method that tries to prove the sub-goals that this first command generated automatically, and that apparently worked, and then this done says, oh yeah, this is the end of the proof. So how can we see what's in there? Well, let's first questions about the definition of add. No. Then let's look at the lemma in detail, what's going on there. And now it's again helpful to look at the output window. So we let's look at both at the same time. And if you now position your cursor on or behind the first lemma, the statement line, then down there you see the reaction of the system. The system says, okay, you have started a proof now, and what you want to prove is the following numbered sub-goals, the following numbered proof goals. And in this case, you have only one thing to prove, namely the thing that you've just stated, namely that add of m and 0 is m. And so now the next line, the induction, will refer to, in this case, the first sub-goal, the one and only formula that you're trying to prove. And what is the result of the induction statement or the induction proof method? It's 2 lines. So now, after the induction, you have to prove 2 things. You have to prove the base case, and you have to prove the induction step. And so the base case is exactly what you're used to. You replace the induction variable by 0, and you have to prove that add of 0 and 0 equals 0. Well, that is, of course, a direct consequence of the topmost line there. But we haven't got there. And the next line, the next sub-goal number 2 down here, that consists of the induction hypothesis, namely that what you want to prove is true for m, and then the step that from that you have to prove that it's also true for the successor of M. So that's the way induction on natural number works. You have to prove a base case with 0, and you have to prove a step where you assume that the statement you're proving holds for some variable, and you have to prove that it holds also for the successor of the variable. And the next line, auto says, please, system, try and prove this automatically. And then the system, luckily in this case, knows sub-goals. So that means it could prove both goals, and you're done. And the done is documented by explicitly saying, and this is the end of the proof. So you have to write that, otherwise the system will complain. So why was that automatic? I've already said why the first line is trivial. And the second line, well, let's look at it in detail in a moment on the slide. So this is nice that it's automatic, but it's also nice if you can understand why it's automatic, and that requires a little more detailed explanation of this proof. It's not a long proof, but at least I want to show you how you would write it in a more verbose, readable style. So far, questions about what happened here, except for why it was proved automatically? And then that's the end of that theory. And most of our proofs in the first 2 weeks will be of this form that you do in induction and then auto, maybe with some embellishment. But do not be misled. In order to prove interesting things, you need to learn a more complicated proof language where you can really structure your proof in more detail, and these induction and auto proofs are nice for the beginning, but later on we'll have to do better than that. So let's go back to the slides. And this is what an informal proof would look like. As you would be expected to write on a piece of paper. So you want to prove that add of M and 0 is M. So you prove by induction on M. And you have a case 0, the base case. And there you have to prove that add of 0 and 0 is 0. And that holds by definition of add. And then you have the case suc of M, the induction step, where we assume that add of M and 0 is M. And we call that the induction hypothesis. And I will usually refer to this by just IH. And we need to show this, that if you now have a successor of M, it still works. And the proof is as follows. It's just the first line from here to here. It's just the definition of addition if the first argument is a successor. And then from here to here, that's the induction hypothesis, because now you can replace the subterm add of M0 by M by induction hypothesis. And that would be the form that you would be expected to write it in a normal textbook style. Now, with these simple proofs that we have, auto can do these things automatically, but later on, in particular when we talk about things like complexities, then usually these proofs are not so automatic anymore. And then there is an Isabelle alternative how to write such sequences of equations and inequations. At the moment, we don't need that yet, but it'll come. Question about that proof, the natural numbers? Yep.
When we are working on proofs, should we always stick with prefix format? Or
what do you mean by prefix format?
Like plus A, B, or can we...
No. I mean, if you have an infix symbol, please use it as infix.
Okay.
I mean, the system will also echo things in infix form if both arguments are present. Okay, so lists. That's, of course, bread and butter for functional programming. Lists of elements of type A are called A list. That's the type. And this is how the type is declared. The type of A lists, well, the elements can either be nil, meaning it's an empty list, or it can be a cons of an element and a rest list. So you put an element in front of the list. And this is very similar to what you know from other programming languages, except that programming languages typically have more syntactic sugar, so you don't write nil, but I think in almost all cases you write this. And we'll get to that syntactic sugar, but at the moment actually, maybe we'll get, yeah. Let me just see. Yes, actually it comes here. I don't need to put it on the board. Yeah, so here are some lists. Of course, you start off with nil, then you can make a cons of some element and nil, meaning a one-element list, or a cons of one element and another element and nil. In this case, as elements, I've chosen numbers, and so on, so you get longer and longer lists. And then there is syntactic sugar, like in programming languages. If you write this, it's just a shorthand for writing nil, the empty list. And if you write this, x hash axis, that's a shorthand for cons x axis. So that represents a list with the first element x and the remainder x's. So again, that differs in other languages. So in OCaml, I believe it's colon, colon, is that right?
Yeah.
Yeah. So in OCaml, the hash is colon, colon. In Haskell, the hash is colon. So you see there's a bit of variety there. We've chosen the hash for, well, certain lexical syntax reasons. And you call the first element of the list the head, and the rest of the list the tail. That's just a standard terminology for lists. So these are the good old lists as known from functional programming languages. And you can also write lists explicitly, enumerate them one by one, the elements, and that will just be a shorthand for this. So, of course, use this syntax, and the system will echo things in that syntax, but always remember that inside is just a shorthand notation for a nest of conses. Now, the most important proof principle for lists is induction, and it's similar to induction over natural numbers, except now we also have elements in the list. So in order to prove that some property P is true for all lists, X's, what you have to prove is you have to prove that it's true for the empty list, and you have to prove that if you take an arbitrary element and an arbitrary list, and you assume that the property already holds for the list, then you have to prove that it also holds for the list where you've put one more element in front. So, of course, this is just a special case of what you might call induction on the length of the list. And this is actually, this induction principle is a proof rule in Isabelle, and it would be written like this. And so it's an implication saying you can prove P of x's for all x's if you can prove P for the empty list, and you can prove that P of x's implies P of x cons x's. Now, I didn't say anything about this funny prefix. We already saw that in the induction step in the natural numbers. That is Isabelle's syntax for a system, a universal quantifier that is almost exclusively used by the system. You shouldn't use that yourself. But if you want to read this, you should just read this like fix an x, fix x's, and then prove that P of x's implies P of x cons x's. So that means they're just like local variables for that particular implication. And this is because you need to make sure that you're proving the induction step not for some item that's already present in the context, but for some really new list and some new item, or some arbitrary list and some arbitrary item, that this implication is true. So this is just, in some sense, context hygiene to make sure that you don't start with something that's already known, but you start with completely fresh and therefore completely arbitrary values, x and x's. And now we get to prove something a little bit more difficult than the addition on natural numbers. We will prove some manipulations on lists. And for that, I will change over here and go here. So now this is merely for demo purposes. The lists are already predefined in main, but I want to really start with bare bones system without lists and show you how to define, how to do how to do some proofs about lists. And therefore, I define the lists again. And if I now ask what is the term nil, the system will give me some very long name, because the system knows now there are two nils there. There's the nil that is already declared in main, and now I've declared another nil. And so the system says, oh, I'm now giving you the full internal name of nil, just to alert you to the fact that this isn't the only nil around. And it's now the fully qualified name. But that's, of course, terrible to look at. And since we're just doing it for demo purposes, what we do now is I insert this declaration that it should use short names, at the risk that if it's a short name, you might not know which of the two nils we're talking about. But since we've just defined nil and cons locally, it actually shadows the other nil and cons. And so whenever we see a nil and a cons, we know it's the local one. And this is not something you should put into your theories. This is just something I'm putting in here to make the demo legible and to make sure that we don't get confused by the already predefined notions on lists. So this is our starting point. We've defined lists the way that they are normally defined. And here you see again, if you look at this declaration, you introduce the cons, and now the types have to be in double quotes. So the cons takes two arguments, and the types of the two arguments are in double quotes. So this is a little idiosyncrasy of the system. Here's the first function definition, the append function, which I've just called app. And it's nothing but a glorified version of the addition function on natural numbers, except that it doesn't add natural numbers, it adds lists together. And if the first list is nil, then you return the second list. And if the first list is a cons, well, then you append the tail of the first list and the second list, and then you put the element or on the head of the first list at the head of the resulting list. So this is very sort of second lecture of functional programming on lists. There's nothing special here. Note that we can't use the shorthand syntax like the square brackets for empty lists, because we haven't defined them. For our list, they really intentionally, we just have nil and cons, so you see the primitive syntax and not a lot of syntactic sugar sprinkled over it. So that's the first function we define. Then we define a second function, the reverse function, which we just call rev. Takes the list and reverses the list. And if you reverse the empty list, of course, you get the empty list back. And if you reverse the list with its head x and tail x's, well, then you have to do a bit more work. First, you reverse recursive. That wasn't what I wanted to do. Here we are. On the right-hand side, you recursively reverse the tail of x's, but then you have to put what used to be the first list, the first element, at the very end. Now, the cons operator puts something at the very front. How do we put something at the very end? We need to use the append function. And we append, you can't just append a single element, but you append a singleton list, a list that consists just of one element. That's what this cons, x, and nil is. So you append the reversal of the tail and the singleton list that consists of the head of the list. And this is the point, the reason why we defined the append function, because we needed it for this second example. And now we want to prove something about it. First, it's always, if your definitions are simple enough, it's always a good idea to check whether they do what you expect them to do. You can do that with a value command. So if you ask what's the value of reversing cons true, cons false, nil, then luckily the system tells you it's cons false, cons true, nil. So at least for that particular list, it works. It also works, in fact, for a symbolic list of two elements. if you ask what's the reversal of cons A, cons B nil, it says cons B, cons A nil. But that's because the definitions are simple enough that you can compute with them symbolically. With more complicated definitions, this may not work. You may really have to give ground values like true and false. Okay, so it seems to be doing the right thing. Now I would like to prove a simple property of reversal, namely that if you reverse a list twice, you get the original list back. And this is the statement of the theorem. Reverse of x's is x's. And the proof principle, well, the only thing we can do here is we can do induction on x's, and then we try auto. But as you can already see, the system complains. It said, failed to finish proof. So your proof script says at that point, I'm done. But in fact, when the system executes these two commands, the induction and the auto, it's not done. So it complains and says, no, proof didn't go through. So this is why there's this red exclamation mark here on the side and also the red underline. So let's look at detail what happened. You have to prove you perform induction. So in the first sub-goal, you've replaced x's by nil. And this will, of course, go through. If you reverse nil twice, you get nil. And in the second sub-goal, we have a proper induction. So this is an induction hypothesis that it works for x's. And then you have to prove that it also works if instead of x's, you have cons 1 x's. And this is the induction step, and the x1 and the x's are really, you can say, locally quantified variables. So this is just a hint to you as a reader. These are local variables and are fresh. Okay, so let's see what auto does. Auto gets rid of the first sub-goal, then the second sub-goal moves up and becomes the first sub-goal, but the second sub-goal was not solved. We still have that same induction hypothesis there, and we have something that looks a bit different. That's not exactly what we had previously. This is what we had previously. That was rev of cons something equals cons something. And now if you perform auto, it's no longer rev of rev, but it's rev of app of rev. So that means auto has done some work, but it couldn't finish the work. And what work has it done? It has basically used the function definition. So it has used the fact that rev of cons is something or other. So it could use that equation, and use means always from left to right. Auto does things from left to right only. So if you look at this situation, and if you look at the inner term rev of cons, then you can see, oh yes, inside on rev of cons, I could apply the definition of rev, and I could rewrite this to an app of rev of x's and cons of the singleton x. So this is exactly what has happened. So the step that was performed was just a single simplification step that turned rev of cons of x's into this rather unpleasant looking term. And then it got stuck and couldn't finish the proof. And now it's your turn to suggest what we should be doing. In most situations, what you need to do at such a point is you need to prove additional properties of the operators involved and make the proof continue. So the question is, can you see any additional property of rev and append that we need to prove in order to make this proof go through? And additional means essentially we've got nothing at the moment. The only thing we've got are the two recursion equations for app and rev, but we haven't got any additional properties. And I will give you a hint what might be useful, because you can see here there's an induction hypothesis that talks about rev of x's. But we can't use that induction hypothesis because inside we have one rev of x's, but the second rev is further away from it. So you can't use that equation here and simplify two revs of x's by x's because the two revs aren't really directly in front of each other, but they're apart. So, question is there some lemma that you can imagine about ref and app that would allow us to manipulate things? Yeah?
You can get the ref inside because it's just like a list. So if you apply the ref on each of those two elements and you turn them around, then it should be able.
Right. That's correct. So I hate this auto indentation. So you're suggesting something of this, I think. Equals
Ref of y s, and in front of it f, and in the back ref of x is.
Yep, I think that will do. Now, that will help us. Let's give this lemma a name. And with these simple lemmas, it's not so difficult to give it a name. With equations, you typically try to come up with a name that is meaningful for the left-hand side. So here, ref app would be a very meaningful name, because the lemma tells you what happens if you reverse an append. A little hint, or not hint, just an explanation. If we had mistyped things or hadn't thought about things very carefully, for example, we might have written this one if we hadn't thought about things carefully. And then what will happen is that the system in the background tries to disprove what you think is a theorem. And in this case, it was successful, and it says auto quick check, that's a subcomponent, found a counterexample. If x's is const some element nil and y's is const some other element nil, then this theorem is false. And so when you see these little blue information boxes, don't ignore them. Typically, they are useful. And in this case, they are useful because they show you that you've made a mistake. And of course, you hadn't made a mistake. You stated the theorem in the correct manner. And therefore, there was no blue box that complained. But that's just in case you see them, you know what's going on. Okay, so then we first have to prove this. Any suggestions of how to prove it? You could just apply auto, but then auto will say, fail to apply the proof method, fail to apply auto, so auto couldn't do anything. So that wasn't successful. I think you know more than most people, so. There are some people in the audience who've been through a similar lecture before, so I don't take their answers.
Induction?
Yes, on what?
On XS and epsilon. YS.
Right, but what does induction on two variables mean? That's not really a well-defined concept. So can you make up your mind which one you want to induct on?
It doesn't make a difference.
Okay, then let's take induction on YS. Okay, and well, actually, sorry, it makes a lot of difference, as you can see. The base case, in the base case, y is replaced by nil, and if you were to make an induction on x's, it would give you very different proof goals. So it may not, in fact, make a difference, but I think it will actually make a difference, and you can't just say it doesn't make any difference which variable you induct on.
It does not here, because in the definition we just swap them and it's more or less.
Well, no, that's precisely not the case. It makes a big difference. If you look at the definition, the two variables are not at all equal. The first and the second argument play very different roles in the definition of app. And that's precisely the reason why it does make a difference. So if you look at the definition of app, what variable would anybody choose to do an induction on? Access. Why?
Because using the definition we can split it.
Yep, that's exactly that. Because if you do an induction on the first argument, then you can use the recursion equations, because the recursion equations expect a nil or a const there. If you do an induction on the second argument of app, it's not going to help you, because the second argument of app is really irrelevant here. There's just a variable there. So it is really crucial that you do the induction on the first variable, on the first argument of app. Of course, that's not. This is not a decision procedure. That's just a heuristic, and the heuristic that typically works well. And so let's see what we do. Apply auto. Let's see what we're left with. And unfortunately, it couldn't even solve the base case. But the base case is easy to solve with another lemma. What do we need as a lemma for the base case? Yeah.
If you append nil, then list stays the same.
If you append nil, but we have that rule. If you append nil, the list stays the same.
If you append nil as the right.
As the second argument, yeah. Yes. So the definition only tells us what happens if nil is the first argument, but if you look at this subgoal number 1, obviously you also need to know what happens if nil is the second argument. And this is what we're going to prove first now. So you can. Let's do that. Or rather, before I do it, maybe somebody... If I write a third equation, app of axis and nil is axis, what do you think the system should say? Or what do you think your favorite compiler would say? Yeah?
It's going to say like unreachable statement or something, because the same pattern would, like the first patterns, one of the first ones would match, because they cover all possibilities of the first argument. And the second argument is just a variable, so nil is also going to match on that before it reaches the hypothetical third statement.
Yeah. So let me just show you what he said. If you write app of axis nil is axis, then it says equation is redundant, covered by preceding clauses. So you can do it, but it's not going to help you, because the system has already analyzed that this case is already defined by the first clauses, because the first argument either has to be a nil or a const, and therefore we don't put it in the definition. In fact, put as little into a definition as possible, prove as much about it as a consequence. Yeah.
What happens if you put that in the beginning?
You can do that, but then it's just going to become a more messy function definition. So why put something into a definition if it's already a fact? So if you put it here, then it will... in fact, it may be that the system still complains that it's redundant. I'm not quite sure. Axis nil is axis. No, it doesn't. But essentially, it's now going to generate actually inefficient code that does much more pattern matching, because the only thing you need to do is the pattern matching on the first argument, and you've now introduced a more complicated second argument pattern matching. So when something can be derived as a consequence, it should be derived as a consequence and not stated, because the simpler your definitions, the simpler your proofs will be. That's the point. So app of axis and nil is axis. if you want to optimize your function, then it may make sense to test for the second one being nil as well. Then you can get, you may get better performance. On the other hand, only for those cases where the second argument is nil. And if the second argument is frequently non-nil, then you do lots of useless tests. So it's, I think I wouldn't do it. I've never seen a functional programmer do it. So how do we prove this? Of course, by induction on x's. And now you can see quite clearly you get the two cases, one where x's is nil, and then it's covered by the first line, the first definition for x's, and one where x's is const, and then it's the consequence comes out of the second definition for app. So yep. No, this is not nice indentation. Yeah. Okay, so we've got this. We should give it a name. Let's call it app nil2. But now we will also have to tell the system to use this equation. It doesn't use equations, it doesn't use lemmas automatically, at least auto doesn't. You have to tell the system. And one way of telling the system, or let me show you if you don't tell the system, what happens. We now go back to the previous ref app thing, and we did induction, we had two subgoals, we did auto, the first subgoal wasn't proved, and it's still not proved because we haven't instructed the system to use this additional information. So what you can do is you can put simp in front of it, and then that means please from now on always simplify any formula that you see with this equation from left to right. And that makes a lot of sense. You don't want to see app of x is nil. You just want to see x's. It's just a simpler term. And so now, hopefully, the first subgoal in the second lemma, induction of x's, auto, that's now disappeared. Okay, so we've got rid of the first subgoal, the base case, implicitly using this new lemma that we've introduced. That's why we've introduced it before and not afterwards. But unfortunately, the induction step still hasn't quite worked out. So these two things should be the same: the app ref well const blah blah blah, and this on the bottom line. And they look kind of similar, but they're not identical. So what do we need to know about the operators involved in here to make them really identical? There's another mathematical property of one of the operators that is missing. And if we knew that, then we'd get it. Yes? Why not? Okay.
That appending is associative.
Yes. So here, these two lines, the two bottom lines, they're almost the same, except that the arguments are parenthesized in a different manner. Here you first append ref y's and ref x's, and then you append at the end the x1. Here, on the other hand, you append the x1 to the reversal of x's, which is in the order, the same order as here, and then you append to the front reverse of y's. So you get the same list out, you just perform the appends in a slightly different order. But you append the two sublists in the right order. First the ref y's, then the ref x's, and then the x1. You just do it, you structure the putting together in different manner. So you need this final lemma, I think it's the final one, app, and now you have to decide which way around you want to state it, and for no particular reason we will state it this way around. So what should be on the right?
App xs, and then in parentheses app ys.
Yeah, that's it. So now we again If you tried auto, it wouldn't do anything. So we can use, again, the same heuristic we used before. It's a good idea to induct on something that's the first argument of an app. And here axis is a good idea because it's there as a first argument. And here it's again as a first argument. So it will help us twice. You could also argue, why don't we use y's? Because y's is also occurs as a first argument to app. Conceivably, yes, but sort of the numerical odds are in favor of x's because y's only occurs once as a first argument, but x's occurs twice. So that lends some weight to the induction on x's. Of course, on the other hand, you can just try, and if it doesn't work, you try the other one. So it's perfectly okay to be a bit experimental here. Induction on x's. And then apply auto. And indeed, yes, it worked. And so now we can put the done after it. And it also makes sense to turn, well, that's debatable. Do we always want them to be parenthesized in one direction if you have nested apps? I think you want that. So, but that's less clear cut because the term doesn't really become any smaller. So if you declare something a simplification rule, you should always think about it. Is it going to do me any good or not? In this case, it's probably going to do us some good. So it certainly helps us in the next lemma. So let's call this app assoc or something like that. And let's give it the simp status. So now, from now on, it'll be used as a rewrite rule from left to right every time the system applies auto. And now, let's see if we finally get to prove this one, which was the one we got stuck on. Yes. So we now have the ref app. And in order to use that in the next proof, because remember, that's what we really set out to prove, the ref. So make that also a simp theorem and done after it. And now the ref goes away. So it can be a lengthy process. And in particular, it was lengthy here because you started from ground zero. There was no knowledge about the functions except their definition. And you had to build up all the further properties by hand. In many situations, there will already be a large background library, and you will just have to incrementally prove one or two lemmas. But this is quite representative of a larger development where you really need to build up a lot of information in order to get somewhere.
I have a question.
Yes.
Do we have to use simp, or can we apply the ones explicitly?
You can apply them explicitly, and why don't I tell you about it now? So, for example, you might think this is not something you always want to happen. And then you can do the following. You don't make it a global simp rule, but you say, when you call auto, you say simp, and then you give the name of the lemma. That was ref app, I think. And then it also works. And that is, in fact, preferable if you have lemmas that are not really, you don't want them to be used every time. Yeah.
And
no, you can continue.
Okay, so also with that apply, what arguments are valid arguments to this apply?
That we will find out as time goes by. So at the moment, we just know about induction and auto. We will have more proof methods as we go along in the course.
I have a question because I already used either a bit. And what is the difference between simp and simp add? Is simp only applies the...
In this case, there's no difference. You could also write simp add. This is just a shorthand. The simp, but it's a bit. There's some subtleties there. If you don't use auto but you use simp, then it looks different again. So we can. I've explained your question, but we may come back to it when we explain simp. Yeah. Okay, if there are no further questions, then let's finish with the slides. That was the informal proof. No, I won't go through that one. So this demo was really just for demo purposes. And you should really use the basic lists that are already there, and they are already in main, and you don't have to reinvent lots of stuff, just reuse what's there. And in particular, note that we already have an append function, that's the infix ampersand, and we have a length function, which does the obvious thing, and a math function, which is something crucial for functional programming. So you can find lots more stuff in that theory, but I think this is already will get you a long way. So now I want to finish the lecture with telling you a little bit about numeric types, because they might not be so important early on. I think we will concentrate mostly on natural numbers, but later we will also have the reals, and there you need to know some basic facts about it. There are three numeric types, nat, int, and real. They're also the complex numbers, but we don't use them in this course. You need to convert explicitly from one type to the other. So it's not like a subtype system where one type is a subset of another. It's like in a programming language where when you go from int to real, you have to apply a function to do it. And so you have the function int that converts the natural number to an integer, real converts the natural number to a real, and if you want to convert int to a real, there's a special one, real of int. And please, if you want type real, you have to start from complex main rather than main. If you start from main, there's just int and nat in there, not real. So this is in case you need real. You don't use main, use complex main. Now, you need, yeah?
I have a question. Reals, have they arbitrary precision? Or?
The reals are the reals as God made them. So, same as the natural numbers and the integers. So this is mathematics. In the programming language, we also use the natural numbers and the integers, and they are again infinite precision. You can't use the reals in the programming language, not those reals, because they are, the mathematical reals. You have to put in those conversion functions, but you don't have to put them in by hand. Isabel tries to insert them automatically if you're in the context of complex main. And there might be multiple ways to insert them to get a type correct term, and then Isabel will choose an arbitrary one, and if you don't, you might get into trouble then. I mean, I'm not asking you to put in everything by hand, but I'm just warning you, if you don't put everything into by hand, then sometimes the system may put it in the wrong place, and later on in your proof, it's suddenly the conversion function is in the wrong place, and your proof becomes more complicated. So here's an example of what I mean. If you write I and say I must be an integer, and you add n, a natural number, to it, then of course this is not type correct, because the plus function expects arguments of the same type, so we'll have to put in a conversion function, and it's quite clear what we have to do. We have to convert the natural number into an integer, and then you can add the two together, and that's exactly what the system will do. So if you write this, the system will convert it already into that. And you don't have to write the colon int and nat if from the context the int and the nat are already, that type is fixed. If, on the other hand, if you write this, n plus n, and n is a natural number, and you explicitly say, oh, here I want a real, the whole thing should be a real value, then there are two possibilities. You could either add the two natural numbers and convert it into a real, or you could convert each natural number into a real and then add them. And at that point, the system will choose an arbitrary one of the two possibilities, and it will echo. I mean, the system echoes the version it has chosen, so you see what's happened. But I'm just warning you that you should look at what the system made of your term. Otherwise, maybe you get into problems. So, what functions do we have on these numeric types? There are also coercions in the other direction, but they are not put in automatically. So you can turn an integer back into a natural number with function nat, and that's not put in automatically because that may do strange things to, for example, negative numbers. What is a negative number interpreted as a natural number? In this case, it's always 0, but that's an arbitrary decision. And then there are the floor and the ceiling functions that you should be familiar with. And then we have the basic arithmetic functions that are all overloaded. Addition, multiplication, binary minus. We have a unary minus as well, also overloaded. For division, it's a bit more, there are two divisions. There's one discrete division on natural numbers and integers, and they are called div and mod. And then there is a division on real numbers, and that is with a slash. Now, why haven't I written real here? Because that division is again overloaded, so it doesn't just work on reals, it also works on complex numbers, and it works on many things, not just the reals, but it doesn't work on nat and int. Whereas nat and int, this one is also generic. That doesn't just work on nat and int. It also works on other types, but not on the reals. So depending on which numeric type you are facing, you should either use the discrete division or the continuous division. And then we have two exponentiations as well. One with a natural number. So the first argument is the base, and the second argument is fixed to be a natural number, and it's just basically this stands for iterated multiplication of the base this many times. And then we have an exponentiation which is for real numbers, where both the base and the exponent can be real numbers, and this is the infix power operator. So again, these are two quite different operators. And then there's an absolute value function. You don't have to learn this by heart, but this is a table you can go back to when we come to the point where we use real numbers. And all the binary operators up here are infix. So that's the summary of the numeric types and the functions you have there. Now let me just summarize what we learned in the lecture today. So we saw a data type command for defining possibly recursive data types as data in Haskell or type in OCaml. We saw a fun command for defining possibly recursive functions by pattern matching over the data type constructors. So this is very similar again to functional programming. And we'll go into more detail next week. And we saw, so far we've only seen two proof methods. One is induction, where you give a variable and it performs induction on that variable, and the induction schema depends on the type of the variable. So the system will look at the type and say, oh, this is a list, then we do structural induction. This is a natural number, then we do induction on natural numbers. And we have the auto-proof method that just tries to prove all the subgoals there are, and it tries to prove them mainly by simplification, meaning that it tries to use the function definitions and the simp lemmas as simplification rules from left to right. Yeah, this is really important. And it simply does it. Equality, of course, is a symmetric operation. But in order to reduce the search space, it's only used in one direction by the auto method, which makes it incomplete but fast. And the general schema of proofs so far is you state the lemma with the name and then the actual statement in double quotes, and then there's just a sequence of applies, and once you've proved it, then you explicitly put a done there to show that your proof is over. Now, this is not really a nice proof in the sense that it's not readable for a human. We will see more readable proofs later on, but in the beginning we will concentrate on this apply style. And only if the lemma is really suitable as a simplification rule, you always want the right-hand side, left-hand side replaced by the right-hand side, then is it advisable to add the simp thing there. And something I haven't shown you, I should have shown you that, you can already, if you state a lemma, you can already assume the lemma by writing sorry as the proof, meaning for a moment, I'm not giving you the proof, but accept the lemma. And then you can see in your later proof steps, in your further lemmas, whether this will actually help you. Because it can be the case that you assume you prove some lemma, and then later you find, oh no, this lemma doesn't help me at all. I've wasted lots of time proving something that isn't helpful. If you first assume it with sorry, and then go on and use it, then you will find out quickly if it was helpful or not. On the other hand, this can also be misleading because then you assume something which is wrong and it helps you in your proof, but when you go back to prove it, you find out it's wrong and you can't prove it. Then you've also wasted time. And that's the usual problem with bottom up and top down. There is no golden road to proofs. You have to combine bottom up and top down. It's the same in programming. If you build a wonderful library and people say, but we don't need any of these functions, you've wasted your time. If on the other hand you build some on top of some framework and then it turns out that framework is not implementable, then you've also wasted your time. So yeah, it's just a, you have to find some compromise. And yeah, this is what you can do with this sorry. And for the proof stage, let me just explain this again. These are what the proof states of the subgoals look like, and that just means these are your assumptions, this is your conclusion, and these are local variables typically introduced by the induction. And yeah, and it may be, depending, you have to set a particular something in the interface. So then these implications here are shown like this. On my in my installation, I've done this because I find this more readable. It clearly separates the assumptions from the conclusion. You will probably see it like this in the tutorial that is also on the in the material. There's a hint on how to get that notation out rather than this one. But in the end, this is also readable. And if you use this notation, you see this notation, simply read the semicolon between the assumptions as an and. But this is really just shorthand for this. And that's it. Yep, I've kept to my allotted time. So thanks a lot for turning up this early on Friday morning. And good luck with the tutorial later on. And I hope to see as many of you as possible back next week.